So, chi-square tests. Chi-square tests are a measure of dependence, okay? We're seeing if one variable depends on the other variable, okay? Guaranteed to get this in an exam, usually around 10 marks, okay? The hypothesis test is always two-tailed, okay? We're just checking for any association. So we're checking for dependence or independence, okay? Very first thing you do when you get one of these questions is add a totals, okay? So we add the totals for the columns and the totals for the rows. Okay, so 193, 212, 95, 54, 110, 184, 152, and 500. So both of those should add up to 500. Okay. Now is probably a good time as any to talk about the critical values. Okay. So the critical values, just like with a correlation hypothesis test, we need to get them from the table. Okay. So we've got a formula sheet which looks something like this. Okay. And we'll see on the left hand side we've got this Greek letter nu, okay, which is like a fancy V. Okay. The fancy V, nu, stands for the degrees of freedom. Okay, so in AS, the degrees of freedom is reasonably straightforward. Gets a little bit more complicated in A level. Okay, the degrees of freedom is if I now have these total columns. Okay, if I get rid of, say, that row and that column there. Okay. I can still work out what are in those cells there, okay? Because I've got the totals, so I can just take them away, okay? So that means these are not independent of these, okay? So that is just another layer of dependence. So what we say is that the degrees of freedom, which we call nu, so we've got nu here. So degrees of freedom, so if this is an n by m table, we do n minus 1 times by m minus 1. Okay? So the degrees of freedom for this would be, because this is a 4 by 3 table, that's going to be a 3 by 2. So our degrees of freedom is 6. Okay? We're doing this at a 5% level. So if we look at our formula sheet, we have the 5% level is actually the 0.95 level, okay? This is because from the shape of the graph, probably x less than or equal to x equals p, I need to work out the 0.95 level here, okay? So 5% level, nu equals 6, 5% level, then we get 12.59 as our critical value, okay? So 6, 0.95, 12.59. Okay, I'm going to make a note of that now. So our critical value is equal to 12.59. Okay. So when we do a hypothesis test with a chi-squared, we have some things we need to work out. These values here were given in the question. We call these our observed values. Okay, so they're observed, call them, say, OIs. Okay, then we need to work out our expected values. Okay, our expected values are if these two variables are independent, then what should we expect there to be in each cell? Okay, so if they are independent, then I can use the formula of independence from probability. So if they're independent, probability of A times by probability of B is probably A and B. Okay, that's if they're independent. So if I'm, say, looking at this value here, okay, the value we expect to be in there is going to be the total, so 500 times by the probability of being an adult times by the probability of buying a theme park ticket. okay, the probability of being an adult is going to be 212. Oh, other way around. Messed that up already. Is going to be, oh no, I was right, 212 over 500. That's the probability of being an adult times by the probability of being at a theme park. 110 times by 500. And then because we want an expected frequency, we're going to times it by 500. Times by 500. Okay? We can simplify this because those 500s can cancel. Okay? So the expected value of this one would be 212 times 100 divided by 500 gives me 42.4. No, it doesn't. It gives me 46.64. Okay, that is the expected amount in that cell. Okay, so if I was working out, say, this value here, to work out the expected amount, I would do the probability of being a senior, so that is 95 out of 500, times by the probability of being a combined one-day total ticket holder, so times by 184 over 500, then times by 500 again. Okay, if I put that into my calculator, so that gives me 95 over 500 times by 184. Gives me an expected value of 34.96. Okay, so we call these values the expected values. Okay, you can see that this expected value is quite close to the observed value, whereas this one is quite far away. Okay, this is essentially what a chi-square test is doing. It's seeing how far away is our expected value from our actual value. Okay, so to work this out, we need another table. We need another table of expected values. And the way we find our expected values, so for my EI, I would just do the row total times by the column total divided by the actual total. Yeah, which should just come from row, column divided by total. Okay, I'm going to just quickly pause it now and do up the table of expected values. Okay, so here are now my expected values, so EI. Okay, now to work out our chi-square value, we just do our observed values, take away our expected values, square it so that we don't care which one is bigger, and then divide it by our expected values. Okay, that gives us how far away our observed and our expected are. So for our chi-squared value, we do the sum of the individual values. So observed take away expected squared over expected. So for example, if I want to work out the chi-squared value of this one here, so I would do the observed, so 70, take away the expected, 71.024, squared divided by 71.024. That gives me that chi-square value of 0.0148. Okay, and you just repeat that for all the values and then add them up. Okay, so yes, it is a bit time consuming, but these are high mark questions. You're given plenty of time to do them. So if we add up all these values, all these chi-square values like this, so we get a final chi-squared value equal to 17.02. Now, just like in a correlation hypothesis test, we compare our calculated value to our critical value. So because our chi-squared value is bigger than our critical value, then we reject H0. and then we have our summative statement at the end. Yeah, there is sufficient evidence to suggest that there is an association between ticket type and age group. Okay, that's the basics, but there are a couple more nuances as well. So here is another example here. So here is data from a company deciding whether there is an association between the age and the mobile phone operator they choose. So this is a sample of 500 people. So here are the observed values. I've worked out the expected values as well, and these are all the expected values. You wouldn't be expected to work with a table this big. This will take too long in an actual exam, and they've got many more questions to ask you otherwise. One of the main nuances with a chi-square test is this part here. Okay, so the expected values need to be bigger than or equal to 5 in every case. So here are my expected values, and they all look good apart from this one here. Okay, that is 4.62. If I have an expected value less than 5, I need to combine either a column or a row. Now, it's usually very obvious which one you need to do, whether we're combining a column or a row, but sometimes you can have a choice. Then it's important to have a look at what the question is asking. So if this question is there an association between age and mobile phone operator? If I combine the rows, so I combine this one to make a 40 plus row, that's not going to give me enough information to decide whether there is a dependence. Yeah, because that 40 plus section will be far too big, so it will be a pointless thing to do. So here I'm going to combine these two columns here. So the virgin is going to go with other, so I just have more in the other. You then don't need to recalculate everything, you're just going to combine the values. So you're going to combine the observed values, so that observed value is going to be 12, that one 18, etc. And then combine the expected values. Then do our chi-square test as normal. Okay. I'm going to put up a question for you to try and my answer with it as well, and then we'll get into the special case of 2x2 contingency tables. So here's another question here. This is data saying the age and number of accidents for drivers, and I want you to test at a 2.5% level. Does age have any effect on the number of accidents drivers have in a year? Okay, so just pause, have a go at it, and my answer will be up very shortly. So here is my solution here. Remember, the first thing we do is add the totals on, so I've added the totals on. Then we work out our expected values. Our expected value, row total times column total divided by total. Here all the expected values are bigger than or equal to 5, so there's no combining required. Then I need to work out my degrees of freedom. This is a 4x3 table, so it's going to be 3x2, which equals 6. Find my critical value from the table, and I get 14.45. Work out my chi-square value, so observed, take away expected, squared divided by expected, add them all up, I get 17.1. Because my chi-squared value is bigger than my critical value, I reject H0, then I have my summative sentence at the end. So there is sufficient evidence to suggest an association between age and number of accidents. Okay, that is a perfect answer to what would be most likely a 10-mark exam question. So on to Yates' correction, which is the special chi-square test we do when it's a 2x2 table. So Yates' correction is used exclusively when we've got a 2x2 table, okay? And here it is. This is not given to you in your formula book, so you need to memorize it. Okay, so we have our observed values, take away our expected values in a modulus. So we're just taking the absolute value of that. Remember, in our calculator, we would just use the absolute value there, so it's above the left bracket on this calculator. Take away 0.5, then square it, divided by expected values. where this formula comes from is because we're essentially trying to get a discrete and continuous distribution to match, so we need to do a little correction. This is well above the scope of this course, so do not worry about it. All you need to do is memorize it and be able to use it. So here we've got a question. Responses to a question in a survey are as follows. Test at a 5% level whether there is any association between gender and response. So everything starts off the same. We find our totals. So I add in the totals. So I've got 87, 113, 85, 115, and they both add up to 200. Okay, I work out my expected values the same. So my EI, so I essentially got yes and no, and I've got male and female. So for this one, I'm going to be doing 87 times by 85 divided by 200. So 87 times 85 divided by 200 equals 36.975. 36.975. Yeah. And then I can just work out this one really quickly. We're just doing 85 take away it, because this row is still going to add up to 85. So if I just do 85 take away 36.975, that gives me this value here being 48.025. Okay. Then I can work out this one really quickly as well, because I just do 87 take away that. So if I do 87 take away that, I get 50.025, and then do the same here. So I'm going to do 115 take away that one. So 115 take away 50.025 gives me 64.975. Okay, so it's actually easier to work out the expected values for this one, because you only really need to work out one, and then you can work out the other ones. Right, so chi-squared values. So we've got yes, and we've got no, and we've got male, and we've got female. Make that look like an F. Okay, so for this first one here, we're going to do the observed, so 34. First we're going to put in the brackets, so absolute, so 34 take away 36.975 minus 0.5, close the brackets and square it, and then divided by 36.975. Gives me a value of 0.1657 to 4 decimal places. 4 decimal places is plenty. Okay, do the same for the next one. So that would be 51 take away 48.025 divided by 48.025. 0.1276. Okay, and then doing the same process, that one will be 0.1225 and this one will be 0.0943. And when we add them up, we get a chi-squared value equal to 0.51. Once we've got our chi-squared value, everything else is still the same. I need to work out my degrees of freedom. This is a 2 by 2 table, so the degrees of freedom is always going to be 1. So I'm only interested in the top column here. So degrees of freedom is 1, we're doing 5% level, so our value is 3.841. So degrees of freedom is 1, critical value is 3.841. Then we do the test as normal, so our chi-squared value is less than our critical value. That means we accept H0. So there is insufficient evidence. To suggest an association. Between gender, and response. Remember, you always have to put it into context. Okay, and that's it. So a 2x2 will take you less time, but you need to memorize the formula. That's the payoff. I'm going to put another one on the board, and I'll put the answer on shortly after that. And then the last thing we need to talk about is goodness of fit tests. So here's the question. We need to test at the 5% level whether these figures here support the claim that taking vitamin tablets help prevent colds. Over to you. So here is my answer. I've noticed that in the previous examples I didn't actually write what H0 or H1 is. Okay, so H0 and H1 is always H0 is no association. H1 there is an association. Okay, and always in context. So as normal, add the totals on, work out our expected values. So work out the expected values here. Again, remember you only really need to work out this one. So this one would be 80 times by 82 divided by 200, and just work out the other ones by taking them away. So that one's 80, take away 32.8. This one's 82, take away 32.8, and that one could be the other totals, take away one of the other ones. Degree of freedom is 1. Critical value is 3.841 because we're doing it at 5% level. Add up the chi-square values. Yates, I get 3.866. Chi-squared bigger than critical value. Reject H0. Sufficient evidence to suggest an association between colds and vitamin tablets. Right, on to goodness of fit, just the last thing, and then we're done for chapter 6 on chi-squared. So here we have a goodness of fit test, which is predominantly in the A level, but you can be asked it in the AS. So a goodness of fit test at AS level is just checking whether the results are in line with a ratio given. Okay. The only thing which changed here is how to work out our degrees of freedom. So there is this formula which is given to you where the degree of freedom is the number of bins, take away the number of constraints. Okay? Constraints are much more of a thing at A level. So if you have to estimate anything, so for example for a binomial, if you have to estimate P from a table, then that is an extra constraint. Here at AS, we're just going to have the number of categories take away 1, because your only constraint is your totals, hence your degrees of freedom. So the national results for SATs are in this percentage. The head teacher at primary school with this data here wants to know whether their results are in line with the average. So first we need to do is do our expected frequencies. So I have my observed values already, so these are my observed values. Now I need to work out my expected values. So you're either going to be given a ratio or a percentage table like so. So we've got 120 people in a sample here. So if I want to work out my expected values, this one would be, I expect 6%, so it would be 0.06 times by 120. This one would be 0.01 times by 120. 0.2 times 120, 0.46 times by 120, 0.27 times by 120. Okay, we get 7.2, 1.2, 24, 55.2, and 32.4. Our usual rules for a chi-square test still apply, so I've got an issue. That value there is less than 5, so I need to combine. If it's a goodness of fit test, combining is easy because I've only really got one option. So I'm going to combine these two values here. So now I'm going to have a new column essentially, which is going to be no level /2. With a combined frequency of 4 and a combined expectation 8.4. Then I work out the chi-squared values as normal. So I use my normal formula, OI minus EI squared over EI. So 4 take away 8.4 squared divided by 8.4. That gives me here 2.3048, 2.0417, 0.6094, 2.1778. A reminder that the bigger value you get for each chi-squared means the more dependence there is in each cell. So this one is adding the most weight to my chi-squared value because it's got the biggest. This one is adding the least amount, so it's the closer to what we expect. Add those together, I get a final chi-squared value of about 7.14. So my chi-squared value equals 7.14. My degrees of freedom is my number of categories take away 1. So here I've got 4 categories. 1, 2, 3, 4 and 5. So that's going to be 4 take away 1 is 3. I work out my critical value, so it's 5% with V equal to 3. So 0.95, V equals 3, 7.815. Then construct the test as normal. I haven't written the hypothesis again. I'll add that in later. So chi-squared is less than my critical value. That means I am accepting H0. So my final sentence is insufficient evidence to suggest that the school is not in line with the national average. Okay, so my H0 here should have been that the school is in line with the national average. H1, the school is not in line with the national average. So here I do not have enough evidence to say it is not in line. So this is an average school from this data. And that's about it for Chapter 6 AS chi-square tests.